Good morning, class. We are looking at exam 3 review covering chapters 3 and 4, 3.9 to 3.11, 4.1 to 4.5. This is part 4, covering 4.3 through 4.5. 4.3, how derivatives affect the shape of a graph. 4.4, indeterminate forms and L'Hopital's rule. 4.5, summary of curve sketching. So starting with 4.3, the synopsis of that is given here, how derivatives affect the shape of a graph. So a function is increasing where f prime is positive and decreasing where f prime is negative. So when we look at this, this is a curve, but if you thought it would be a line, it looks like a line with a positive slope. This one, a line with a negative slope. Needless to say, it's not a line. So slope is the derivative of a linear function. That's why f prime positive versus f prime negative. A critical point is defined as the point at point C where f prime is either 0 or does not exist. DNE, does not exist. A relative max or relative mean is a critical point at the top or the bottom of an interval of a graph. So peaks and valleys, if you will. A function is concave up, where f double prime is positive and f prime is increasing. A function is concave down, where f double prime is negative and therefore f prime is decreasing. So concave up versus concave down. An inflection point is a point where concavity changes. Inflection points occur where f double prime is 0 or does not exist. So looking like that, where the concavity changes, is a location known as IP. So to continue with the graph, I want to remind you of what we learned in previous courses as far as the graphing is concerned, like college algebra, pre-calculus. So the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. So when f of x is given a sub n, x to the power of n plus a sub n minus 1, x to the power of n minus 1, all the way to a sub 0, the first term, because it's in descending order, it's called the leading term. And ultimately, the graph will look like this function. So here's what's happened. We either have even power or odd power. We either have a sub n is positive, meaning the leading coefficient is positive. So it looks like ultimately like y equals x squared. So when x goes to negative infinity, so does y. That means the second quadrant. When x goes to positive infinity, so does y. F of x is y. If a sub n, the leading coefficient, is negative, then it looks like minus x squared. And in the case of an odd power, this looks like, for example, y equals x cubed. X goes to negative, so does y. Y goes to negative infinity, and x goes to infinity. F of x goes to negative, and this is for down here. So let me fix that. Actually, I think this is x squared. This is minus x squared. This is x cubed. This is minus x cubed. So this one is just infinity. Okay, and this one is minus. Okay. So I want to make sure that one is understood, and we take it from there. All right, so that's the concept known as the end behavior. We also have a behavior near an x-intercept, which is also near a 0, and it depends on the multiplicity. If the 0 has the formula x minus c to the power of m. M is the multiplicity. If m is odd, f will cross the x-axis at that point. If it's even, it won't. So for example, in this case, it's odd and it crosses for a linear function, and it's nonlinear. Also, it crosses this, both of them are odd, but whereas here it can't because the multiplicity is even. The higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function. So this is just to quickly refresh your memory as far as the graph of this function is concerned. We want to graph f of x equals minus x cubed plus x squared plus x. And what I want to do, I want to quickly show you how to graph it with the information from a pre-calculus. And then we add calculus to that. So to do so, first and foremost, we are going to factor out. We can factor the x, or better yet, let's factor out the negative x. The reason I factor out the negative x, because I want this to have a positive coefficient in case it can be factored. This can't be factored. So I'm going to use the quadratic formula x equals minus b plus minus the square root of b squared minus 4ac over 2a. And for this part, I'm going to write a equals 1, b equals -1, c equals -1. So when we put it into this formula and we evaluated what we get, 1 plus minus square root of 5 over 2, which means now we have 3 zeros. I want to make sure everybody's following what. This gives us 0, that means 0, 0. And this gives us 2 answers, which means the following. 1 plus square root of 5 over 2 comma 0, 1 minus square root of 5 over 2 comma 0. And this is both the x as well as the y-intercept. So if I were to graph this just the way it's given with the information I have, I would put all those zeros, of course, 0, 0. And then if I look at this one, in order to put it on the graph, 1 plus square root of 5 divided by 2 is close to 1.6. Again, decimal, you can put it into the calculator and evaluate it. 1 minus square root of 5 over 2 is about 0.6. Negative, okay, so somewhere here. The end behavior basically look like minus x cubed, which means we are in the second and fourth quadrant. So this is the end behavior. Those arrows represent the end behavior because the degree is odd, n is 3, which is odd, and a sub n is -1, which is negative. So the graph will look like something like this. It's going to go down, and at some point it has to come back up. You may not know how far it goes because now we're going to use a calculus to figure out. This goes up, but it has to come back down. And now we know that all of them, all of these, each and every one of them has a multiplicity 1. So in each case, it crosses the x-axis. It's a rough sketch. And by the way, you can always pick up a couple of points, maybe a couple of points between these 2 zeros, a couple of points between these 2 zeros, to have a better graph. But that's what we did in pre-calculus. And now we are going to use calculus to find max and mean. So I'm going to clean up the mess, and I'm going to go through that using adding calculus. All right, so in order to do the first step, all we have to do, we are going to take a derivative of this function, which gives us negative 3x squared plus 2x plus 1. We set that equal to 0 to find the CPs, short for critical points, and if we take the negative out, makes it possible to factor it in this fashion. I'm hoping everybody is comfortable with the factoring. So when we set f prime equal to 0, we get two answers, 1 and negative 3. And so now we are going to do the first derivative test, which means we're going to go with the number line, and we are going to put these values in order. So the number line goes from negative infinity to positive infinity. The smaller of the two numbers is first, the second one is second. And at negative 1/3, f prime is 0. At positive 1, f prime is 0. And so we use what's called TP, for short test points. TP stands for short test points. And so, for example, here I can put negative 1 as a test point, 0, 2. But honestly, if you check, one of them is good enough, simply because if you go back here, each one has a multiplicity 1, so they alternate. If I put the 0 in here, it's easiest. Gives me plus 1. So if this is plus, these two alternate to negative. And again, you can just plug in, for example, negative 1 into here or here, observe, positive 2 into here or here, and observe. You get the sign. So to have a better understanding, I'm going to throw in arrows. So negative arrow down, positive arrow up. So down and up, this is a local mean. Up and down, this is a local max. So the local mean takes place at x equals negative 1/3. The local max takes place at x equals 1, which means we are going back to the original function, plug in those values to find the y coordinate because we want the pair. So 1 is easy. If I plug in 1, this becomes negative 1 and 1 cancel each other. This becomes 1. So 1, 1. So the maximum local max is equal to the y coordinate 1 at 1, 1. And you want to answer that accordingly when they ask you. Now, if I plug in negative 1/3 and I do that, I have to evaluate it. So let's plug in negative 1/3 into the original function. Negative 1/3 to the third is negative 1/27. With negative becomes positive 1/27. This one is positive 1/9. This one is negative 1/3. The common denominator is 27. We end up with minus 5/27, which means the local mean is equal to this value at this pair, negative 1/3 and negative 5/27. So the first derivative test gives us a lot of information. Furthermore, it is increasing in between negative 1/3 and 1. It's decreasing from negative infinity to negative 1/3, union 1 to infinity. And as you can see, the first derivative test not only gave us the relative extrema, also intervals of increasing, decreasing. Now, this is the information from the previous page. Here's the function, here's f prime, here's the intercepts, here's the max and mean. Now we are going to find f double prime, which makes it what? Let's calculate this right from f prime. F double prime is minus 6x plus 2. And if I set this equal to 0, x becomes positive 1/3. Now I'm going to do the sine graph again from negative to positive infinity, and I put however many. There is only one point that makes that 0, so we put it here. And so we do the test point to the I'm going to use again TP for short. To the left of 1/3, let's say 0. To the right is 1. And again, that's a very easy case. If you plug in 0 into f double prime, makes it positive 2. So it's positive here. It alternates, or just plug in, you see it's negative here. So what it means is that over here, from negative infinity to 1/3 is concave up. From 1/3 to infinity is a concave down. Okay, concave up here, concave down. Because of the change, 1/3 is the location of I pure inflection point. What is the y coordinate? Go back to the original function. Go back to the original function, evaluate it at 1/3. So 1/3 cube is 1/27. This makes it negative. This is plus 1/9. This is plus 1/3. And again, 27 is a common denominator, 11/27. I'm assuming we can add them up easily. Therefore, the IP takes place at the pair 1/3, 11/27. Now, we want to graph this, and I like to, write the summary here. So starting with x-intercept 0, 0, here 0, 0. 1 minus square root of 5/2 is about negative 0.620. We do that for the sake of graphing. This is a precise answer. This is an approximation. So this is 1. This is negative 1. So minus 0.6 is somewhere here, close to here, right? 1.62, this is positive 1, somewhere here is positive 2. So roughly here it's that 1.6, 1.62. Maximum takes place at 1, 1, here's 1, here's 1. So put them together. And because it's a max, I'm going to put a double arrow, meaning it can't cross that. And that's the thing that we can find using calculus, and we did. So this is something we can't find it without calculus. The IP takes place at 1/3 and 11/27. We're going to go with the rough estimate of 0.3 and 0.4, so 0.3, 0.4, so somewhere here. The minimum occurs at this pair. Again, we go with the decimal representation for the sake of a graph. Minus, let's say, 0.3 roughly, so minus 0.3 here. And then coming down to 0.2, so somewhere here. Okay, this may not be to scale. And again, remember the end behavior. So it looks like that. Again, because it's a minimum, I put a double arrow just like that, putting them all together. This is the final answer. So I hope everybody is comfortable with that. So what calculus does for us, it gives us the location of a mean, local max. And here's the inflection point where it's concave up to here, and it's concave down. So this is where it starts changing. It took a lot of time, but it was worth going over the whole thing. Okay. The next topic is indeterminate forms and L'Hopital's rule. Limits of the following forms are indeterminate forms. There are many different formats: 0/0, infinity over infinity, or some of them. For example, if you look at this one and you plug in 1, ln of 1 is 0, this is 0. If you plug in infinity, this is infinity. Ln of infinity is infinity. This is infinity minus 1. By the way, infinity minus 1, infinity times 10, square root of infinity, infinity squared, infinity times 2, infinity divided by 10,000. All of them are infinity. And so the L'Hopital's rule basically indicates if the limit is such that we end up with one of those formats. This is telling us we end up with 0/0, infinity over infinity. Then we can use the L'Hopital's rule, which says if we end up with this format or this format, we can take the limit of the same thing. Instead of f of x, we use f prime. Instead of g of x, we use g prime of x. That is the L'Hopital's rule. And those are not the only indeterminate forms. There are other indeterminate forms. So here's the synopsis of that. Again, I wrote that. And another example would be, for example, 0 times infinity. Because I want to make sure we understand what's happening. Because there's a struggle. When we say 0 times infinity, remember, we are looking at it from a limit point of view. So when we say 0, it's not necessarily 0, it's getting close to 0. When we say infinity, it means getting close to infinity. That means which one is getting there faster. If the 0 gets there faster, it ends up being 0. If infinity, maybe it ends up being infinity, and maybe somewhere in between. The process is that you write it as f over 1 over g, or g over 1 over f, so it ends up being 0 over 0 and infinity over infinity. But with practice, you figure which one is easier and which one can be easily differentiated. And there are other forms. We will discuss it in a moment. So let's start with what we just mentioned, okay? Ln x over x minus 1 as x goes to 1. The very first thing, you cannot use that unless you show, now I'm going to plug in, okay? You don't have to show this step, but if I remember what we do, we plug in ln 1 minus 1 is 0 over 0. So you can just say it's 0 over 0. Again, you've got to be positive because sometimes it's not. Since this is the case, we can use L'Hopital's rule. So the derivative of the top is 1 over x, and the derivative of the bottom is 1. And as you know, this is really 1 over x, which results in 1 over 1 when we plug in. So it ends up being 1. So 0 over 0 doesn't mean anything. It's indeterminate. If you recall, I've discussed that concept, which means really more work. So you work it out. Let's look at this example. If I replace the x with 0, and I'm going to show you because it's important that you see what happens. So if I plug in here, e to the power of 0 minus e to the power of, again, minus 0 or 0, doesn't matter, minus 2 times 0 over 0 minus sine 0. So I hope you see that the top is 1 minus 1 minus 0. So the top is 0, the bottom is 0. And because we proved it's 0 over 0, we can use L'Hopital's rule. Meaning, we're going to write the same limit as x approaches 0. We're going to differentiate this itself. Differentiate this is e to the power minus x times minus, with this becomes plus. This becomes minus 2. This becomes 1 minus cosine x. Let's plug in. So if we plug in, what happens? This becomes 1, right? Because it's 0. This becomes 1, right? E to the power of 0 minus 2. And this is 1 minus cosine of 0, which is 1. So it's 0 over 0. Again, I'm hoping we have no problem with basic trigonometric functions and common arcs. I can use the L'Hopital's rule again. So this becomes itself, this becomes e to the power minus x times minus 1, which makes it minus e to the power minus x. 1 gives you 0. Remember, the derivative of cosine is negative sign. With this negative makes it positive sign. Let's plug in 0. If I plug in 0, e to the power of 0 is 1, minus e to the power of minus 0. That means, again, e to the power of 0 is 1, and sine of 0 is 1. Sine of 0 is 0, my apologies. And so 0 over 0. Again, we are going to use L'Hopital's rule. The point of this question was to show you can repeatedly use the L'Hopital's rule. This gives you itself, this becomes plus, and sine gives you cosine. Again, I'm assuming those are easy differentiations by now. So now, I want to make sure we understand this. So I'm going to show you. So what we have here is e to the power of 0 plus e to the power of 0 cosine of 0. E to the power of 0 is 1. 1 and 1 is 2. Cosine of 0 is 1. So 2 over 1, or simply 2. So it ends up being 2. Okay. So we used L'Hopital's rule in abrupt times. By the way, I put H here just to represent L'Hopital's rule. In many texts, they use this one. Everybody pay attention. In many texts, they use equal and they put the H at top. That means they're using the L'Hopital's rule. That's just the notation I wanted you to be exposed to. All right. For this example, if I plug in, I get 1 minus sine of pi over 2 cosecant pi over 2. Now, sine of pi over 2 is 1. So the numerator is 0. And cosecant is 1 over sine, so 1 over 1. So 0 over 1 makes it 0. What is my point? The numerator becomes 0. It doesn't mean you can use the L'Hopital's rule. You have to look at the bottom also. So you can only use the L'Hopital's rule if you first show this is the case or this is the case. We have seen this before. So this, if you plug in, you get 0 over 0. So what I want to show you, what we did before, we used our technique of factoring. So we can factor the top and the bottom into x minus 2 x times x plus 3 and x minus 2. So factoring will do the job. And if you replace the x, you get 5. You get 2 plus 3 equals 5. However, this can be done by L'Hopital's rule also simply because we say the 0 over 0, just for the sake of argument. If I go with the L'Hopital's rule, this gives me 2x plus 1, and this gives me 1. If I plug in 2 times 2, 4 plus 1, 5 over 1, I get to the same answer. Now that we are exposed to L'Hopital's rule, we can do it either way. But I just wanted to remind you of the method we had learned before. In this example, if you replace the x with infinity, ln of square root of infinity. Square root of infinity is infinity, ln of infinity is infinity, infinity squared is infinity, so you have infinity over infinity. It's in this format we can use L'Hopital's rule. Now, how do you differentiate the natural log? You flip this over and then times its derivative. That's one way to do it, or you can change that. I will discuss that in a moment. This one, 1 over square root of x, and then times 1 over 2 square root of x, and this is 2x. I'm assuming by now everybody remembers this. Okay, so everybody remembers that this is x to the power of 1/2, and to differentiate, you get 1/2 x to the power of negative 1/2. I'm referring to this part, okay? I'm hoping we're okay with that. You can also write this one as ln of x to the power of 1/2 or 1/2 ln x and differentiate it that way, which means 1/2 times 1 over x. Either way is fine. I thought this was simple enough. I did not cut it into that format, but you can do it as you wish. Okay, I will finish that in a moment also. And so what happens is that the numerator is 1 over 2x. The denominator is 2x, and complex fraction becomes 1 over 4x squared. Remember, we are not losing the limit. That's extremely important. The limit of 1 over 4x squared as x approaches infinity. And obviously, since the denominator is huge, it becomes 0. Now, if we go with this route, I want to make sure that we understand this second method, okay? So we could write, let me use a different color here, limit as x approaches infinity of 1/2 ln x over x squared. So I'm going to write equals and h. That means we proved it's infinity over infinity. So I'm going to use the L'Hopital's rule. So the limit as x approaches infinity, here's the second method. So 1/2 times the derivative of ln x is 1 over x, and the denominator is 2x. This is the part that has been differentiated, okay? And so I hope you see that. Let me use a different color. This is equal to the limit as x approaches infinity of 1 over 4x squared, which is 0. So I wanted you to see both methods. Okay, so it's maybe an easier method, you know. Again, I didn't bother with that because square root of x was simple enough, but it's your choice. All right, let's move on, and we want to find the limit of x times ln x as theta approaches 0 from the right, and this is the indeterminate form of 0 times infinity. And the technique is to take one of them down and make it 0 to over 0 or infinity over infinity, because L'Hopital's rule only applies to those. So if we plug in, we get 0 here. I want to make sure that you know, if I plug in, I get 0 times ln of 0 from the right is important because class, I hope you remember the graph of a function y equals ln x. Okay, and the domain is 0 to infinity. 0 is not included. That's why we have the plus sign here, 0 from the right. And therefore, this is 0 times ln of 0 from the right, so 0 times negative infinity. Now, of course, when we look at this one, 0 times infinity or negative infinity, who cares, the same concept. So we are going to take either x down or ln x down. I can say x over 1 over ln x, or I can say ln x over x. When you want to rewrite that, you want to consider which one is easier to differentiate. If I take the ln x down, okay, I want to make sure you understand that. If I take the ln x down, I can write 1 over ln x. And that's difficult to differentiate. But if I take x down, I can write it as 1 over x. So x can be 1 over x. Now, again, let me just write this. If you wrote limit as theta approaches 0 from the right of x over 1 over ln x, there is nothing wrong with this, except it's more difficult to deal. That's the point, okay? And even that one, you can work it out. Even that one, you can work it out. But as I mentioned, it's a lot more difficult. So in this case, ln of 0 from the right is negative infinity. 1 over 0 from the right is a positive infinity. Whereas here it becomes 0 over 0, okay? So you can use L'Hopital's rule on both, but we want to use it on this one because it's easier. Why is it easier? Because now if I use the L'Hopital's rule, this gives me 1 over x. And by now, I think we know 1 over x gives us negative 1 over x squared. If you have any doubts, class, this one you can say x to the power of -1, and then differentiate it minus x to the power of -2 or -1 over x. Now, this is obviously a complex fraction. If you multiply the top and the bottom by x squared, and I'm going to assume everybody can do that, we get the ln of minus x as x approaches 0 from the right, which is 0. So the point being, you have to go through the process to figure out what happens, okay? Here's another example, square root of x e to the power minus x over 2. And I hope you see you can take this one down or this one down. First of all, this is infinity, and this is e to the power minus infinity, which is 0. I hope you see that why this is 0. Let me just show that, and I'm going to erase it. So this, if you were to plug in, you would get square root of infinity e to the power of minus infinity over 2. And I hope you realize e to the power minus infinity, or doesn't matter, infinity over 2, it's 1 over e to the power of infinity, which makes it 0. Because a to the power of minus m is 1 over a to the power of m. This has got to do with the exponential rules. Hopefully we are comfortable with that. So with that being the case, we get infinity times 0. Infinity times 0, we can take this one down or this one down. Because this one has a negative exponent, if we take it down, it becomes positive exponent. It's easier, and it's infinity over infinity, because this is square root of infinity, which makes it infinity. And this one is e to the power of infinity over 2, makes it infinity. So again, fairly simple, okay? And now we can use the L'Hopital's rule. Now, I have discussed this square root of x before, and I've shown you. So the derivative of that is 1 over 2 square root of x. So we're going to use L'Hopital's. This one is itself, and remember, times, maybe I write this so it becomes clear. This one is e to the power of 1/2 x. So if you differentiate, you get e to the power of 1/2 x, and then times 1/2 or divided by 2. So this is how you do the math. 1 over 2 square root of x is the power of x over 2 times 2. And we simplify the complex fraction. We multiply these two, we put it at top. We multiply these two, we put it at the bottom. These two cancels out these two. And we end up with this. I'm assuming we can simplify any complex fraction. Now, if you plug in, each case goes to infinity at the bottom. So this becomes infinity, this becomes infinity, 1 over that is 0. This happened to be 0 also. All right, now indeterminate form of the type infinity minus infinity, try to convert the difference into a quotient by using a common denominator or rationalization or factoring out a common factor, so that we have an indeterminate form of 0 over 0 or infinity over infinity. So for example, the limit of cosecant x minus cotangent x as x approaches 0 from the right, okay? So it becomes cosecant of 0, cotangent of 0. And remember, cosecant means 1 over sine. Sine of 0 is 0, that goes to infinity. And cotangent of 0 from the right. I hope you remember the graph of cotangent, okay? That is also, so both of them are positive infinity. So I want to make sure we understand, if the question ends up giving us, if it ends up giving us infinity plus infinity, the answer is infinity. If gives us minus infinity is again minus infinity. But infinity minus infinity, that is indeterminate. And you need to know your basic trigonometry. So we're going to write cosecant as 1 over sine and cotangent as cosine over sine, and take a common denominator of sine x. If we plug in 1 minus cosine 0 over sine 0. Cosine 0 is 1. So 1 minus 1 is 0. Sine 0 is 0. So 0 over 0 requires, we can use L'Hopital's rule, which means we're going to differentiate the top over the bottom. So the limit as x approaches 0 from the right, the derivative of 1 is gone. Cosine is negative sign with negative makes it sine x, sine gives you cosine x. And when x approaches 0, sine becomes 0, cosine becomes 1, or you can even say tan of 0 is 0. You can change that to tangent, or you can just plug in. Either way, the answer is 0. To continue, let me clean up. And we want to take this limit. It involves natural logs. So if we plug in, I hope you see that infinity to the power of 7 minus 1 is infinity. Ln of infinity is infinity. The same thing here. Infinity to the power of 5 minus 1 is infinity. Ln of that is infinity. So you're looking at infinity minus infinity. But we're going from 1 from the right. I thought it was just infinity. My apologies. So 1 from the right makes this 0. If we plug in this, let me write that, we get ln of 0, but it's ln of 0 from the right. And if we plug it here, the same thing, minus ln of 0 from the right. And I have shown you the graph, remember? So ln of 0 from the right is negative infinity. So negative infinity minus negative infinity makes it minus infinity plus infinity, and therefore we have an indeterminate form. We have an indeterminate form. Let's clean up the mess. And so what is the technique here? The technique here is to combine these two, ln of the quotient, x to the power of 7 minus 1 over x to the power of 5 minus 1. And the limit of this, you can interchange because the continuous function after 1. Remember, the domain of natural log is 0 to infinity. And so this makes it from 1 to the, in fact, because it's x to the power of 5 minus 1 is from 1 to infinity. So we can interchange those, and we deal with this expression. This expression, if you plug in 1, this becomes 0, this becomes 0. So you're dealing with 0 over 0. So ln of 0 over 0. And this 0 over 0, you can use L'Hopital's rule. So L'Hopital's rule, we're going to differentiate the top, becomes 7x to the power of 6, and the bottom gives you 5x to the power of 4. And since x is approaching 1, this becomes 7, this becomes 5. So this becomes 7 over 5, ln of 7 over 5, which is an exact answer, everybody. Ln of 7 over 5 is an exact answer. And that's the final answer, which is practically done. So infinity minus infinity ends up with 0 here, but in this case ends up with some number, ln of 7 over 5, which is a number. And again, you can use a calculator to see the approximation. All right, how about secant minus tan x? And if you plug in pi over 2, remember secant is 1 over cosine, and that makes it infinity because pi over 2 on the left, that means this means we are in the first quadrant, okay? Close to 90 degrees or pi over 2, but in the first quadrant. So this means first quadrant, okay? Less than 90 degrees, everybody. And so secant, and again, secant, just in case, it's 1 over cosine. And remember, cosine is 0. So 1 over that makes it infinity. And the same thing happens with tangent, which is sine over cosine. Okay, remember, tangent of pi over 2, like in this case from the left. like 89.999 degrees. That is also infinity. So infinity minus infinity. First, notice that it is infinity minus infinity. Okay. Secant goes to infinity and tangent goes to infinity as x approaches pi over 2 from the left. That means less than 90 degrees. So it's indeterminate, and I'm going to change the secant to 1 over cosine and tangent to sine over cosine again to use a common denominator of cosine x. So the numerator becomes 1 minus sine. So one technique is to find a common denominator. As you can see, if I plug in sine of pi over 2 is 0, cosine of pi over 2 is 0, so we get 0 over 0. So sine of pi over 2 is 1, 1 minus 1 is 0. Cosine of pi over 2 is 0. So sine of pi over 2 is 1. Okay, if you plug in, get 1 minus 1 over 0, which is 0 over 0. So L'Hopital's rule. I'm going to take the derivative of the top. This gives you 0 minus sine gives you cosine x. So minus cosine x, cosine gives you minus sine x. And you can plug in. This, by the way, is the code in case. This is cotangent x, or you can plug in. The top is 0, and the bottom is -1. 0 over -1 gives you 0. Or you may know cotangent x is 0 when it gets closer and closer to pi over 2. Just in case, here's the graph of y equals cotangent x. Okay, just to refresh your memory. Again, some basic trigonometric functions we are supposed to know. Indeterminate forms and L'Hopital's rule we're going to continue, and we may end up with the following format. The limit of f of x to the power of g of x as x approaches a. If both of them are 0, we get 0 to the power of 0. If one of them is an infinity, the other one is 0, is infinity to the power of 0. And if f of x, this is 1, the other one is plus minus infinity, so 1 to the power of infinity, and so on. So each of these 3 cases can be treated either by taking the natural log, let y be f of x to the power of g of x, then ln of the left side is ln of the right side. So g of x times ln of f of x. So by writing the function as f of x to the power of g of x, remember, f of x, we can write it e to the power of ln of f of x g of x. So e to the power of g of x times ln of f of x. And in either method, we are led to indeterminate product of g of x times ln of f of x. We're talking about this part, which is the type 0 times infinity or infinity times 0. So that's how we deal with that, okay? Using one of those methodologies will give us the answer. Here's an example. If we look at the limit of 1 plus sine 4x to the power of cotangent x as x approaches 0 from the right. So when x is 0, sine becomes 0, so the bottom is 1. And cotangent, even if you remember from the graph I just gave you in the previous page, it's 1 to the power of infinity. So we are going to call this something, let y represent that. Therefore, we can take a natural log of both sides. So ln of y is ln of the right side. And that means cotangent x becomes a coefficient. When you take a natural log of this one, okay, so ln, and this one sits in front. That's what we have here. And cotangent is 1 over tangent. So we can divide it by tangent. So we deal with the limit of this piece now. And when we are done, whatever we get, remember, we want to go back to this. whatever the answer is, the answer to this one will be e to that power. So whatever this ends up being, the answer to this would be e to that power. So we want to take the limit of ln y as x approaches 0 from the right. We're going to take the limit of this piece as x approaches 0 from the right. So when we plug in 0, this becomes 0. Ln of 1 is 0. Tan of 0 is 0. By the way, ln of 1. Okay, everybody remembers 0, I hope. So 0 over 0 means I can use L'Hopital's rule. And so I'm going to write the same limit, and I'm going to differentiate the top over the differentiation of the bottom. The top is a natural log. First, I'm going to flip this over. I'm going to flip this over, and then I'm going to multiply by the derivative of this, which is 0 plus sine becomes cosine of 4x times 4. Cosine of 4x times 4. This is 4x. Okay. Cosine of 4x. It's important. That was it. There was a typo, everybody. And tan x, derivative is secant squared. And so what happens is that if we plug in 0, this becomes 4 times cosine of 0, 1 plus sine of 0, because 4 times 0 is 0, and secant squared of 0. Now, as you know, cosine of 0 is 1, so this is 4, this is 1. Secant is 1 over cosine, that is also 1, and the answer is 4. So even right here, if you say, okay, so the answer to this limit is e to this power, I'm okay with that. That's the end of the story. But just to refresh your memory as far as why this is the case, we want this limit. And this is the limit of y as x approaches 0 from the right, which, remember, y is the same as e to the power of ln y. Y can be replaced with e to the power of ln y. And we know that this is equal to 4. Therefore, the answer is e to the power of 4. Or just right here, you can say the answer to this one is e to the power of 4. That's, again, fine with me. All right, summary of curve sketching, vertical asymptote. I'm going to go over new stuff just in case, just to refresh your memory about rational functions, vertical asymptotes and horizontal asymptotes, short VA and horizontal asymptotes HA. This is HA. Okay, so it was just again a typo, HA. And a rational function is in the form of p of x over q of x, where p of x and q of x are polynomials. That's the definition. I hope you remember that. Where q of x can't be 0, so domain, you set this equal to 0 and you exclude that. That's how you find the domain. For vertical asymptote, by definition, the limit of f of x is either infinity or negative infinity when a approaches from the left or from the right or both. That makes x equal a is the vertical asymptote. In short, set the denominator equal to 0 and solve. So the limit of f of x as x approaches a, or a from the left or a from the right, is one of those. X equals a becomes a vertical asymptote. That's a definition from calculus. But again, a short methodology to do that, set the denominator equal to 0 and solve. The graph of a rational function never crosses a vertical asymptote. It may intersect its VA, simplified, not. Okay, the thing I want to explain about here, if you have a rational function, first we have to simplify it, meaning there can't be any common factor between the top and the bottom. And that gives you VA, because if there is a common factor, you drop it, and that creates a hole when it comes to a graph, not a vertical asymptote. Definition of a HA or horizontal asymptote, okay, the horizontal asymptote y equals f of x or y equals z. If the limit of f of x as x approaches negative infinity or positive infinity is some number, then y equals L is the horizontal asymptote. The graph of a rational function may or may not cross a horizontal asymptote. And again, that's the definition. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. And we have the oblique or slant asymptote, y equals mx plus b. If you take a limit and it becomes mx plus b, then taking the limit of f of x as x approaches either negative or positive infinity. So this is the synopsis of that. And what I want to do, I want to just remind you how we do that in general. So what I like to do for a function y equals a sub n x to the power of n all the way to a sub 0 over a sub m x to the power of m all the way to b sub 0. The degree of the numerator is n. So if n is less than n, we have a horizontal asymptote y equal to 0. If n equals m, then we have a horizontal asymptote y equals a sub n, a sub n over a sub m. I'm talking about this part, okay? And if n is equal to m plus 1 precisely, we have a oblique asymptote. Oblique asymptote, just to give you a general concept. So I hope you see that in this example, obviously the vertical asymptote x equals 1, and there is no horizontal asymptote because the degree of the numerator is larger. The degree of the numerator must be less than or equal. So when we don't have a horizontal asymptote, if the degree difference is precisely 1, as it is the case here, we have a slant or oblique asymptote. So we do the division by any means, long division, synthetic division. I'm assuming everybody remembers this. So you divide x squared by x, you get x. X times x minus 1 gives you x squared minus x. You subtract it, this goes away. This becomes, when you subtracting, this becomes plus x minus 4. You divide this one by this one, gives you 1 times x minus 1. This is the remainder, x plus 1. So therefore, y equals x plus 1 is your slant asymptote because, let me erase this, because f of x is x squared minus 4 over x minus 1, which makes it x plus 1 plus minus 3 over x minus 1. And this, y equals mx plus b, is your oblique asymptote, also known as slant asymptote. Let me look at the last example. Here's the function. F of x is x minus 1 over 2x plus 1. And we want to sketch the graph of the function, starting obviously with basics that we have learned. Okay, so we start with the intercepts. And to find the intercept, x is 0, find y, y is 0, find x. So if you set y equal to 0, that means f of x is 0. A fraction is 0 when the top is 0, x becomes 1. So I want to make sure we understand what's happening here. To find the x-intercept, we set y equal to 0. This is y. F of x represents y. A fraction is 0 when the top is 0, x equals 1. So 1 comma 0. Y-intercept, set x equal to 0, you get minus 1 over 1, which is simply negative 1. So we have the x-intercept at 1, 0, the y-intercept at 0, negative 1. Asymptotes. Vertical asymptote is easy. 2x plus 1 equal to 0, x equals negative 1/2. you have to write an equation. You can't say asymptote is -1/2, x equals -1/2. It's a vertical line. So again, this is roughly x equals -1/2. Horizontal asymptote is y equals 1/2. And there is no slant asymptote. Why is that? Look at the degree of the numerator. Degree of the numerator is 1. Degree of the denominator is 1. So the coefficients of this is 1, this is 2, 1/2. Y equals 1/2. And whenever you have a horizontal asymptote, you don't have a slant asymptote or vice versa. You have only one of it. So y equals 1/2 is your horizontal asymptote. And as you recall, in pre-calculus, we basically realized that we can have this piece and this piece, or this piece and this piece, because we have these 2 points, obviously, that we want points on both sides of the vertical asymptotes. And since this is the case, it's either here or here. You just pick a point on the left side, you have the graph. But we want to add the information from calculus. We're going to find the derivative and the domains. And so the domain, obviously, you said this one equal to 0, x equals -1/2, or you have it here, and you exclude that. So the domain, here's one easy way to write that, but a more proper way of writing this, everybody, a more proper way of writing this, using interval notation, -∞ to -1/2 union -1/2 to infinity, and you're excluding -1/2 because you're using parentheses. So let's differentiate and see what happens, because we are interested in finding a local extrema, intervals of increasing, decreasing, so on and so forth. So this uses, so this is f, this is g, so we are going to use f prime g minus g prime f over g squared, the quotient rule. So this gives us 1 times 2x plus 1 minus this gives us 2 times x minus 1 over the bottom squared. So that is the differentiation. I hope nobody has any problem with. This gives us 2x plus 1 minus 2x plus 2. And as you can see, the numerator simplifies to number 3. Now, right here, you may recognize that this is always positive, except and remember, x can't be -1/2. So why is this always positive? I want to make sure we understand what's going on. Well, you have a fraction. The top is a positive value. The bottom is something to the power of even 2. So that makes it always positive. When is it that it's not? When x is -1/2, the expression is undefined. So if you recognize that, that's good enough. But if you don't recognize it, you want to go with the sign graph class. At -1/2, x is -1/2, f prime doesn't exist. To the left of -1/2 is positive, and so is to the right, because to the if you go with the test point TP, you can pick 0 here, 1 here, and if you put it in here, you see in both cases becomes positive. So what does it mean? Because there is no change, there is no extrema, there is no local max, there is no local mean, and it's always increasing. However, you can't say it's increasing from -∞ to +∞. You can say it's increasing from -∞ to -1/2 union -1/2 to infinity, because it's not consistently from negative to +∞. It's not one piece of graph. It's not a continuous function everywhere. That's why it's the case. As far as the concavity is concerned, we go with f double prime. So I'm going to assume you can differentiate this. And to differentiate this, it's easier to write f prime is 3 times 2x plus 1 to the power of -2. Anytime the numerator is just a number. It's easier not to use the quotient rule. So 3 times -2, the same thing, the power of -3, and then times 2 by the quotient rule becomes -12 2x plus 1 to the power of -3, and it becomes this. So let me erase that. -12 over 2x plus 1 cubed. Now we are dealing with a different story. This is not even, so things can happen. So if you go with the graph here to the left of -1/2, we can pick a TP of 0, -1, -1, and to the right is 0. And if you plug in 0, which is easy, this becomes a positive, this becomes negative, right? -1 makes it positive. So what does it mean? Positive means concave up from -infinity to -1/2. Negative means concave down from -1/2 to infinity. And -1/2 could be an inflection point if it was part of the domain, but it's not. Remember, it's not part of the domain. If it was, that would be an inflection point. It's not. So just, by the way, it is important to set the horizontal asymptote, which is 1/2, equal to the function, and solve it and see if there is a part where the graph crosses the horizontal asymptote. And the good thing is it doesn't. Okay, in this case, it doesn't. Therefore, you can graph it as these two parts. By the way, for this one, you can pick any number to the left of your vertical asymptote, -1/2. For example, if you pick -1, so let x be -1. So the numerator is -2, and this is -1, and it's +2. Okay. Now this is not to scale, but you can locate the pair -1, comma 2, and that would be your graph.